In the 1980s, there was an AI resurgence when researchers at Carnegie Mellon created one of the first self-driving cars. The vehicle was steered by an artificial neural network called ALVIN. It was similar to the perceptron, except it had a hidden layer of artificial neurons between the input and output. As input, ALVIN received 30 by 32 pixel images of the road ahead. Here I'm showing them as 60 by 64 pixels. But each of these input neurons was connected via an adjustable weight to a hidden layer of 4 neurons. These were each connected to 32 output neurons. So to go from one layer of the network to the next, you perform a matrix multiplication. The input activation times the weights. The output neuron with the greatest activation determines the steering angle. To train the neural net, a human drove the vehicle, providing the correct steering angle for a given input image. All the weights in the neural network were adjusted through the training so that ALVIN's output better matched that of the human driver. The method for adjusting the weights is called backpropagation, which I won't go into here, but Welch Labs has a great series on this which I'll link to in the description. Again, you can visualize the weights for the 4 hidden neurons as images. The weights are initially set to be random, but as training progresses, the computer learns to pick up on certain patterns. You can see the road markings emerge in the weights. Simultaneously, the output steering angle coalesces onto the human steering angle. The computer drove the vehicle at a top speed of around 1 or 2 kilometers per hour. It was limited by the speed at which the computer could perform matrix multiplication. Despite these advances, artificial neural networks still struggled with seemingly simple tasks, like telling apart cats and dogs. And no one knew whether hardware or software was the weak link. I mean, did we have a good model of intelligence, we just needed more computer power? Or did we have the wrong idea about how to make intelligent systems altogether? So artificial intelligence experienced another lull in the 1990s. By the mid-2000s, most AI researchers were focused on improving algorithms. But one researcher, Fei-Fei Li, thought maybe there was a different problem. Maybe these artificial neural networks just needed more data to train on. So she planned to map out the entire world of objects. From 2006 to 2009, she created ImageNet, a database of 1.2 million human-labeled images, which at the time was the largest labeled image dataset ever constructed. And from 2010 to 2017, ImageNet ran an annual contest, the ImageNet Large-Scale Visual Recognition Challenge, where software programs competed to correctly detect and classify images. Images were classified into 1,000 different categories, including 90 different dog breeds. A neural network competing in this competition would have an output layer of 1,000 neurons, each corresponding to a category of object that could appear in the image. If the image contained, say, a German Shepherd, then the output neuron corresponding to German Shepherd should have the highest activation. Unsurprisingly, it turned out to be a tough challenge. One way to judge the performance of an AI is to see how often the 5 highest neuron activations do not include the correct category. This is the so-called top 5 error rate. In 2010, the best performer had a top 5 error rate of 28.2%, meaning that nearly a third of the time, the correct answer was not among its top 5 guesses. In 2011, the error rate of the best performer was 25.8%, a substantial improvement. But the next year, an artificial neural network from the University of Toronto called AlexNet blew away the competition with a top 5 error rate of just 16.4%. What set AlexNet apart was its size and depth. The network consisted of 8 layers and in total 500,000 neurons. To train AlexNet, 60 million weights and biases had to be carefully adjusted using the training database. Because of all the big matrix multiplications, processing a single image required 700 million individual math operations, so training was computationally intensive. The team managed it by pioneering the use of GPUs, graphical processing units, which are traditionally used for driving displays, screens, so they're specialized for fast parallel computations. The AlexNet paper describing their research is a blockbuster. It's now been cited over 100,000 times, and it identifies the scale of the neural network as key to its success. It takes a lot of computation to train and run the network, but the improvement in performance is worth it. With others following their lead, the top 5 error rate on the ImageNet competition plummeted in the years that followed, down to 3.6% in 2015. That is better than human performance. The neural network that achieved this had 100 layers of neurons. So the future is clear. We will see ever-increasing demand for ever larger neural networks.